Hello, it's been a while. Welcome back. And if anyone cares, this is my second update. This is this is the first update. This is the second video I'm making about my TP CPU project. So it's been a while. As I said, it's been a long time. I gave up on programming for a while. I felt demotivated. I didn't really want to do it anymore. But I'm back. I'm working again. I'm programming again. And I'm seeing what I can do, right? And this is what I've been doing. Most of this stuff was achieved a long time ago, but there has been quite a bit that has happened recently. The recent work has been primarily on the text editor, but in general, since the last update, I have actually written an operating system. I didn't actually post a video about it when I wrote most of it, but I wrote a kernel, I wrote a number of file system utilities, I wrote the shell, I wrote tons and tons of stuff for the OS, and it's all tested and working for the most part. There might be little bits here and there that I've forgotten to test, but there's even a text editor now. That's the most recent development in terms of things I've worked on. I've also done example programs, and I've been working on the documentation for the operating system. The documentation should be finished fairly soon. And also I have an assembler that runs within the operating system, right? So I actually have an assembler that can assemble itself running inside of my own operating system. I think that's pretty cool. I think I should talk a little bit about the kernel. Okay, so the kernel is basically just a round-robin kernel, right? It's not very complex in that fashion, right? Its scheduling routine is very simple. However, it does have, through TP CPU, it has memory protection, right? When you switch from from privileged mode to user mode, your view of memory changes, and so you can't access. You literally can't see the rest of memory that the kernel can, and so we have memory protection through that. The biggest thing that I think is unique about my kernel is the IPC system. So basically, okay, hold on. The reason I'm recording this way, right? By the way, is specifically so that I can show you guys stuff. So basically, I have hold on. Okay, this is the right directory. This is the right repo, right? Hold on, let's make clean and cbass ipc.cbass. I'm forgetting what I'm supposed to do. And then cc auto out.c -o3 -o c /ipc. All right, so I wrote this simulator for my IPC system, right? And basically, what I can do is I can simulate a number of senders, let's say 50, sending with a receiver processing time. This is how many cycles of the round robin it takes for the receiver to process something. Let's say it takes 10 ticks, 10 cycles to do it, right? We'll simulate for 1,000 million cycles. I did type that right. 1, 2, 3, 4, 5, 6. Okay. Then for the sender processing time, we're just going to have it be like 3 or something, right? Actually, you know what? Let's up this slightly. So let's do it like 30, right? It takes 30, and let's do 10 million. Right? Hold on. /IPC. There we go. So at the after the simulation is over, right? At t equals 10 million. It shows me, right, what happened, right? So I can actually display how many times that each process was able to reach the, how many times it won, quote unquote, how many times it was able to send to the receiver, right? And it will show me here who got the most sends, right? Well, it doesn't show me who. It says how many how many times the leading sender sent, and how many times the worst winner sent, right? It also tells me how many times we had a tick, a full round robin where nobody sent anything, but the receiver was able to receive something. Hey, wait a minute. What? Ticks wasted. Oh, this is that. This is that. Okay, what's ticks wasted then? Okay, hold on. I'm forgetting what my own thing is. Hold on. Okay, this is... But where is wasted ticks counted? Okay, this isn't important. What is important is that I've effectively, if it is a live tick, okay, if the receiver is available, and the receiver is sitting here if the receiver was available before it looped over all of the senders, right, then it is a live tick, right? So it's ready for a yeah. But anyway, you get the point, right? I wrote a simulation here of the thing, right? Now I actually wonder why it says ticks wasted 3, but receiver ticks wasted 0. I don't know how that happened. I'm just gonna have to figure that out later, aren't I? Oh, because I divide by the receiver processing time. I see. Yeah. That's why it is. So in terms of ticks in terms of number of cycles that the receiver could have been actually doing something, it was 0 because it was okay. Yes, I can understand. Anyway, it's not important. Anyway, so that's that. I actually tested my IPC protocol through that. I also have syscalls for file system access, right? So all that I can do is I can show you that. Right. So this is the syscall. This is the syscall handler, right? And we have different error codes that are returned by a process, and the error code determines what syscall is being invoked. This is that IPC protocol, by the way. Send mail. I have a kernel patching system, so I have a way that I can take source code and then directly patch it into the kernel. And I actually tested this, right? So hold on, let me go show you guys this, right? So if I go to assembler guide, keep pressing tab. I don't support that. Right, so I have it's running assembler on this file, test.t. Now I have auto-out.trom. Okay, now what it has done, right, is it patched the kernel. Then my kernel extension ran 3 times, and in one of them, my syscall got invoked. Now here's the patch. Oh, hold on. Oh, I need to. Yeah, one problem with the way that I've done this is that it does not know how big my terminal is, so I have to. I use this program to tell the OS. Yeah, by the way, and I just used my history there. I pressed the up key, right? That's the feature of the shell. We'll be talking about that here. Anyway, so here is the kernel patching system. This is an example of the kernel patching system. This is technically one of them, right? This is one of the kernel patches, and then this is the main one, right? This one is the one that actually adds to the syscall handler. This is where we actually do the patch right here. I write in this label. This label here, extension, gets written to, if I open the kernel, hold on. If I go to, right, if I go to the extender spots, right, that's one of them. there's the other one. So this spot right here, there's 6 bytes here that are supposed to be overwritten, and we overwrite them here. And basically, what it does is it means that it jumps to here, right? And this is the printing out extension running, right? It prints out that the extension is running. Then this is the test to see if this is the syscall 0x deadbeef. I just chose that as a dummy code. Deadbeef is an ancient programmer thing. If you're a programmer, you might understand that. And this is the code that gets executed if someone invokes deadbeef, right? And then this is where you would put more handlers, right? You'd put another test, and then you'd put another piece of code to do what the syscall does. And so that's the, and by the way, if you just looking here, right, I'm able to delete files, right? That's a major thing, right? So we have syscalls and kernel patching, and I have a provider system. I don't have an example of using this, but basically, there's 32 slots in the kernel where a kernel where a process UUID can reside. And different processes can ask what each of these slots have in them, what UUIDs they have in them. And they can go and talk to that, they can query that process and then send it IPC messages, right? And that is how you can discover, for instance, a daemon. Like if you had TP-CPU set up to be a networked thing, right? And you had a daemon, which was the networking service, and you had a program that wanted to talk to the networking service. It could find the provider slot that it said was the networking slot, right? It would be a thing that you decided beforehand that this slot 7 is the networking slot, and then it could find out what UUID is in slot 7, then send a message to that UUID, and then it could establish communication with that process. And I realized that maybe I didn't explain that well, but just keep in mind that basically this just means that one process can discover that another process exists and is providing service X. Phobos commander, right? That's my shell, right? So if I go back and I run here, right? I have a shell here. It's a full command line interface, right? And it has these built-in commands. You can pause the video and read the stuff if you want. You can pause the video and read this if you want. I also have these commands in the these are compiled binaries. These are programs I can run. And and I also have environment variables, right? That's part of this, right? I can launch daemons. I haven't written any programs to be a daemon, but the thing is, if I launch something as a daemon like Echo, it'll just not have the foreground, so it won't do anything. I guess I could launch like Dell in the background, right? But that doesn't matter, right? I could delete daemon Dell, and now Dell doesn't exist. All right, so Dell ran in the background and it deleted the delete binary. So now I don't have delete in my operating system. Kind of stupid, but anyway. So you can launch daemons. Let me show you environment variables. So I have this program, dump env. I can also do vars, that's a built-in command. And actually thinking about it, vars is probably the more useful one. Whatever. Anyway, the thing is you can, and it shows you every single variable's name and then its value, right? And each variable is basically a pair of strings. Hold on, what's this? Shell exit message call. Oh, I see. There's a new line there, and then this goes here. Okay. Anyway, so basically, and then there's variables in the environment, right? And the reason that this is useful is that, for instance, if I set my prompt to $, right? And imagine for a moment that I wanted to launch a new shell, so I launch com. Now you'll notice that there's now two programs running. If I launch com again, stat, there's 3, com, stat, 4 programs running, right? These are shells in the background, right? If I launch a shell within a shell within a shell, I want to have variables pass from one shell to another. I also want to be able to pass variable values to programs that are running. If you're familiar with how operating systems works, this all seems pretty obvious to you. But anyway, I just wanted to explain that that's what I've implemented. And obviously I showed you command history, right? If I, hold on, let's launch it again. Yes, I use WSL to run this. Right, if I, you know, command history, right? If I press up, I get L. If I press up again, I get stat. I can press down and get L again. I can take LS. Well, now the last thing in history is LS. So if I press up, I get LS. Up again, L. Up again, stat. If I press up again, it doesn't do anything. Down, L. Down, LS. And if I press down again, there's nothing in the history, so it doesn't do anything. So there's the command history. I have a text editor. Right? I think I already showed that to you. So it's called ED. I know that's a sin. You know that's a programming sin to name something the same thing as a Unix utility and not actually have it be that Unix utility.
You're also not tweaking me up. I think it also comes up.
Right, and so I can edit text files. And so I can, this is text. Right, and I can split lines and stuff. I can merge them. It's pretty basic. There's no mouse support. I can't mouse around, but I can cursor around here. I can backspace and delete files. Not files, lines. Sorry about that, by the way, if you heard that. My dad was complaining about me recording this video late at night. Things I do for you guys. There's no tab auto-completion. I keep forgetting that. This is the thing that you should read if you're just starting out the operating system, right? If you're new, type cat guide. This explains how to set up the operating system and how to, you know. This all explains here what Phobos Workstation is. And hold on. Okay, there. The editor was broken because I set the term dims to be a different size of thing than this. Anyway, then that size of terminal. Anyway, so this is just a short explanation of how to use the operating system for, like, if you're totally new, if you're totally lost. Anyway, so that's that. I also have file utilities. I showed a little bit about that, but I have basically things that I can copy and move files. I can't move a directory, that's not a thing, but I can delete the old directory and make a new one. There's no recursive functions currently. That's a to-do, to make recursive copy and delete. I want to do it, I just haven't done it yet. I have the assembler. I think I showed that, right? I can go in and I can go to assembler guide. Let's go to AS examples. Tut2 hello world. AS header.t hello.t. That's the order you're supposed to type it to enter them in. Now there's a new thing. Right, and now I can print out hello world, right? And this is the correct string. I know it's kind of weird. If I open hello.t, this is the program. I just, this is showing how to write comments. This explains what this does. And, this is a function here. This is prints. So that's the assembler, and by the way, I should mention the iron rod. So basically, I think I showed you this before. but basically you can compile blocks of code onto the compiler, right? And that's what this does, CodeGen, right? CodeGen accepts an identifier, and which is so CodeGen accepts an identifier right here, right? And then it does this, right? The reason that I have this macro operating this way, right? And then this feeds into the compile block macro, and then it calls CodeGen on it, is that I want macros in here to be expanded, which requires that that the text of it be processed before it's ultimately passed to compile block. So that's why that's that way. And this is Iron Rod, by the way, right? This is the Iron Rod metaprogramming system. You have blocks of code that are literally added to the assembler, right? And in this case, the kernel is an assembler, so it's being added to the kernel. And that's how we're able to extend the kernel. And the kernel has internal symbols exposed, which is why we're able to patch in this jump here, right? We patch in an immediate 32 instruction. This is the immediate 32 data, and this is the jump instruction. That was written today, by the way, just a few hours ago. Anyway, so that's that. So that's the assembler, and it runs entirely inside the operating system. I also got a C emulator going, right? So go to the distro, go into Canon PC. This is the canonical emulator written in C. By the way, I have my text editor in Linux set to be mapped to ED as well. I know that's a sin for you guys. Anyway, so basically, this is the canonical emulator. Right, if I go to scroll down, this is the main emulator function. This is setting up the registers, and this is the main dispatch. It's just a switch case. It doesn't use threaded goto. It's not a threaded interpreter. It's just a switch case. And after every instruction, we go to the NOP. We go to NOP, which is right here. This is the macro to define an instruction. As you can see, there are 87 instructions, counting the 0 instruction, halt. I have some SIMD operations that I've defined, and that's what this is for. And this defines the way that the virtual computer talks to my real computer. This defines how it opens files and how it prints to the screen and stuff, and how it reads the keyboard. So I have a C emulator, and this C emulator, by the way, is meant to be. It's meant to be simple enough that a junior programmer can probably reproduce it. So you see the main emulator is less than 1,000 lines. Then this thing is like less than 300 lines. If I go to fxvec, this is all extremely simple math code. I think basically this function right here would probably be one of the hardest ones for a junior programmer to implement, but I give the source code for this, the explanation for how to write this in my documentation. Also, the cross product. Some people don't remember how to do the cross product. Matrix multiplication. Some people might not remember how to do that from middle school or high school or whenever they learned it. Yeah, so there's a C emulator. Iron Rod, I explained this before. It's a scheme for an assembler to extend itself. It should theoretically work on basically any 2-pass assembler. That runs on a platform that runs on itself, right? That runs on the same platform that it targets. If you have an assembler that runs on the same platform that targets, and it's a 2-pass assembler, you can modify it to have metaprogramming through this scheme. And I showed you guys. I use it to patch the kernel. Anyway, so that's the progress, right? It's an amazing project so far, right? By the way, I'm just going to need to rebuild the OS. By the way, that's how you compile the OS if you download it. By the way, it does require CBAS to build it, right? the OS is actually pre-built to work, right? You can compile the C emulator and just run the OS on its own. But if you have Coder's Basilisk installed on your computer and you have things set up, you can do that. You will have to do a special something. If you download this project and you want to do this yourself, you're going to need to redirect. You're going to have to edit .cbas_config and change this to point towards your Coder's Basilisk's library folder. So if I go here, right, this is where I have my libraries stored for Coder's Basilisk. Anyway, so in terms of plans for the future, I want to write documentation. So hold on, let me show you this. I have. You guys are seeing my freaking screenshots. Let's see here. Not screenshots. Where is it? There it is. Okay. Distro docs.odt. So I've been writing this documentation. So basically, if you go through here, right, there's like a list of all instructions. There's an explanation about briefly about how you should design operating systems. Very, very briefly. I know less than a page on operating system design. And then this is the most recent thing I wrote. This is an introduction to the operating system. I'm probably going to write a little bit more, explaining how to boot it and how to get around and stuff. Although the operating system itself kind of does a good job of doing that, I'm kind of worried that the terminal dimensions thing might not be very intuitive to some people, but I think it'll get across to maybe most people. I don't know. I'd have to test with a bunch of people to find out. And I have like code examples. Most of this documentation that I've written here is for implementers, people who want to write a TP-CPU emulator themselves. That's the majority of this content, and that's the majority of the content of this. I probably will make a separate document that talks about this purely from a user's perspective, but purely from the perspective of someone who wants to use Phobos Workstation, rather than someone who wants to write an implementation of TP-CPU. This is still assembling, still building the OS. It's compiling the binaries for the thing. I've also been writing. I wanted to show you guys the other documentation I'm writing. I've been writing in operating system documentation. It's not like Linux, guys. It's not like Linux. So if I view the manual page, for instance, for the assembler, this is the in operating system explanation of how to use the assembler, right? And then I can ed com. This one is a little bit more in depth because this is meant to be like kind of how you break your way into the operating system. You need to know how to use the shell in order to use the operating system. A lot of this stuff is actually reproduced inside of COM itself. I think enough of the operating system is compiled that I can actually, we're compiling the assembler, so I can actually run the operating system now. So if I type help, I showed you guys this before, but a lot of that documentation is here too. And so there's a lot of places where you can find out how to use the operating system if you want, right? And so I've been writing all this documentation. Assembler examples. So I showed you a little bit of this, but I wrote some assembler examples. Yes, we are actually going to go point by point into you're used to this by now. Go to home. No. So basically, if I go in here and I go, for instance, you see there are these tutorials, right? I showed you the Kpatcher example. I think I also showed you Hello World. and I ran Hello World. But I also wrote, for instance, this spinner program, and what it does is it demonstrates a little bit of how to interact with the screen. It demonstrates how to use macros to do a little bit of structured programming. So I define this construct here, loop. It's just an infinite loop. And then I have a macro test thing. I use that at the bottom of the file. This was purely for development purposes, but it also demonstrates a little bit of how to use this thing in assembly. And this is just a simple program that spins in a loop and prints out a spinning slash. This is the animation right here. It's a bar, a slash, a dash, and a backward slash. And if you play these one after the other, it makes a little spinny thing. I don't know, I kind of like it. I kind of like it, guys. And I have another one that makes a lot of spinners. All right. And basically it shows a little bit more how you can use structured programming. I have if, right? And I show you how to create an if construct. I show you how to create a loop construct. While, I actually wrote while. This is loop n times, right? This loops a number of times. It pops a number of times off of the stack. I also have ANSI CSI stuff. This is like the ANSI escape codes. ANSI escape codes are used constantly. The operating system finished building. Finally. Wow, we've been talking that for so long. That's been that. And then I also show how to use macros to save yourself work. And I explain how the scoping works in the assembler. This assembler has scopes, by the way. It has like if you define a macro inside of here, the macro will go out of scope at the matching curly brace. And so I explain, I'm teaching the assembler here. I don't need to get into the nitty-gritty details. I just need to talk to you about that. I'm working on a C compiler. I haven't gotten very far on it. But basically, if I go to include, and then I look at this. So basically, I've started designing the type system for the C compiler. I've basically been studying how C works, mostly using just writing C programs and then like messing around. So if I go planning C study matrices.c, I have this C program here that I've been editing, and I've been trying to find out all the weird things that you can do in C syntax. Notably, with function pointers and multi-level matrices and whatever the hell this is, and this. Both of these are like valid, right? This pointer to const int versus const pointer to int is a very strange distinction. And then I could put const out here if I wanted, and I think that would work. So if I type const, does that work? Yeah, it does work. Okay, so here's the thing. If I type a, you see now it will give a different complaint. Unknown type name a. All right, so I can do that, right, and keep entering things and then finding out what the linter says is an error, right? I don't care about unused variable, obviously, but I would care about things like this type is invalid or expected this but instead got this. And so I've just been testing things inside of C to see what is valid, and I've been I've come up with this so far. And here's the main file where I'm going to write the C compiler. Theoretically, right? I think I'm going to end up breaking it into multiple header files because I don't want to write the entire thing in one file. That would be huge. That would be a really complicated thing. And this is all that's written, by the way. There's no actual like code to parse or to lex or parse or anything. It's not done yet. Anyway, I just wanted to show you guys this. So I'm working on a C compiler. And when I write the C compiler, the idea is that people will want to use Phobos Workstation if for no other reason than to get a super portable C compiler, because C is a super popular language. And basically you can use TP-CPU then, if there's a C compiler, to not only run C programs anywhere, but to compile them from anywhere. And that's a really compelling concept in my opinion. And in the longer term, I'd like to make an extension of Phobos Workstation that is like Windows is as to DOS in the old days, right? You know how back with like Windows 3.1 or whatever, Windows 3.0 at least, I forget exactly what version it was that they switched, but with old school Windows, you could you boot up the system in DOS, and then you would type Windows on the command line, and then it would open Windows. So I wanted to do something like that, where you boot up the system on the command line, and then you type in Phobos GUI or something, or GUI or something to get the GUI program. And then it would be like it might be a desktop, it might be like a Macintosh. I don't know. I'm not sure what I would do for a GUI, but it's thinking, right? I pretty much figured out how I would do sound. That's actually why I added the kpatcher for kill task. Was I needed to be able to have a way when a task dies, extension kernel modules need to be able to extend the kill task function to add new things when a task dies, because there could be resources attached to that task, like OpenGL or OpenAL resources, and that's or SDL2, right? So a keyboard, mouse, game controller. I was thinking of using SDL2 to add a GUI to Phobos Workstation, and the GUI would mainly be kind of a gimmicky thing, but I think it would be maybe very compelling. It could be useful. The thing is, Phobos Workstation's design doesn't really lend itself to like fast GUI programs or anything like that. If I do write a GUI for Phobos Workstation, I'm going to continue the theme of Phobos Workstation in that it's a portable CPU and operating system. So it's probably going to use a software renderer and not OpenGL or something. Or it might use OpenGL under the hood, but it would use a very portable syntax, right? I've thought about this, right? I've tried to come up with a way to make a hardware accelerator. The thing is, if I actually use OpenGL, that makes it way harder to port. So it's probably going to be a software renderer. Anyway, so that's the state of the project. These are my plans for the future. If you guys like the project, you can go on. Hold on, this isn't Firefox. You could go on not GitHub. You can go on codeberg.org, and this is Coder's Basilisk. This isn't TPCPU. Yeah, you'd have to get Coder's Basilisk in order to compile these things, but you can go on here and can download the operating system by cloning this repository in Linux, right? You could probably get it working on Windows through MinGW. I haven't done that. There's been bits and pieces that I've actually set up to be compilable through MinGW, but I haven't gone through and actually tested it. So if you want to run this on Windows, and I realize that's somewhat ironic, but here's the thing: I haven't actually gone through and written the emulator for Windows. I've only written it for Linux so far. So, for instance, in standard IO dev, the way that you access directories is different from the way that you access directories and manipulate stuff on Windows versus Linux. See, is a little bit different on Windows and Linux. Like on Linux, you got to enter this code here, and then on Windows, you don't. I thought there was at least one other difference. I guess that was the only one. Anyway, so basically there's things that only exist on Unix that I use to implement the emulator that only exists on Linux, but there should be alternatives on every single operating system in existence, basically. You just have to find out what they're called and how to use them. Like all this stuff, right, is very Linux specific. It's not very portable. What you really have to do is you have to write a new thing that does exactly what this does using that thing, right? And that's what TPCPU is about, right? You just make a new implementation. The implementation of the emulator isn't actually that hard to make. So yeah, anyway, that's the project. Hope you guys enjoyed. Thanks for watching. And SyncFault, if you're watching, thanks for watching my video. You can say the word spiders to me to tell me that you've actually watched it.